Hello everyone, today we will learn about arbitrary angle together. There are various cyclical phenomena in the real world, and circular motion is a representative of such phenomena. As shown in the figure, point P on circle O rotates counterclockwise starting from point A. How to characterize the change in the position of point P? If we connect OA and OP, we will find that the motion of point P will drive the rotation of OP, thereby forming an angle with ray OA. Once the angle alpha is determined, the position of point P can be determined at any time, so we can use angles to characterize the position of point P. We learned the concept of horns in junior high school. Do you remember its definition? We call a shape composed of two rays with common vertices an angle. This is a static definition, and because it is static, it can only describe angles between 0 degrees and 360 degrees, which has significant limitations. So are there any examples in life that go beyond 0 degrees and 360 degrees? Please give an example to illustrate. You may give examples of gymnastics competitions where there is a 540-degree forward flip and a 720-degree backward flip. Here, 540 degrees and 720 degrees. The quantity has exceeded the range of 0 degrees to 360 degrees. Not only that, the front and rear flip bodies also describe different rotation directions simultaneously. Another student can give an example of two gears meshing together, where the active wheel drives the passive wheel to rotate together, indicating that their rotation directions are different. If the radii of two gears are different, their rotation will also be different. These two examples vividly illustrate that angles between 0 degrees and 360 degrees are no longer sufficient to solve problems in daily life. So it is necessary to expand it, not only considering the amount of rotation, but also the direction of rotation. So we have the definition of high school corner. We call the shape of a ray that rotates around its endpoint an angle, where the starting position of the ray is called the starting edge and the ending position of the ray is called the endpoint. And according to the different rotation directions, the angles are divided into positive angle, negative angle, and zero angle. The angle formed by one of the rays rotating counterclockwise around its endpoint is called a positive angle, and the angle formed by one of the rays rotating clockwise around its endpoint is called a negative angle if a ray does not undergo any rotation. It is said to form a zero angle. In this way, after considering the amount and direction of rotation, we expanded the angle to any angle. Obviously, any angle has a dynamic definition. Not only did we consider the outcome of the angle, but we also took into account the process of angle formation. Adding symbols to angles and using symbols to represent direction gives points a numerical characteristic similar to real numbers, laying the groundwork for angle operations. Let's do the following exercise for any angle. If the angle AOB in the figure is equal to 30 degrees, angle AOB1 is equal to 150 degrees, angle AOB2 is equal to 60 degrees. Can you read these angles in the picture? Let's first look at figure 1. We say that after OA rotates counterclockwise for 2 cycles, it advances another 30 degrees. So at this point, its angle should be 2 circumferential angles plus 30 degrees. The result should be 750 degrees. Because the degree of angle AOD is 150 degrees, the size of alpha should be 360 degrees minus 150 degrees, which equals 210 degrees. Because alpha rotates counterclockwise, its angle should be positive at 210 degrees. And beta is obtained by rotating OA clockwise by 150 degrees, so the beta angle should be negative 150 degrees. Let's take a look at the gamma angle OA. If you rotate clockwise to OB2 and advance 60 degrees, it will be exactly 2 angles. Therefore, its size should be 720 degrees minus 60 degrees, which equals 660 degrees. However, because the gamma angle rotates clockwise, the result should be negative 660 degrees. What is the relationship between the two corners? They have size and equality relationships. Naturally, the positive angle is greater than the zero angle and greater than the negative angle. If both angles are positive angles, the angle with greater rotation is greater. If both angles are negative angles, the angle with greater rotation is actually smaller. If the rotation amount and direction of one angle are the same as those of another angle, we call these two angles equal. These relationships are extremely similar to the relationship between two real numbers, so we ask a question: can two angles be added or subtracted like two real numbers? The answer to whether two corners can be added is obviously yes. We can assume that alpha and beta are two arbitrary angles, and we define that the terminal edge of angle alpha should be rotated by angle beta. At this point, the corner corresponding to the final edge is alpha g beta. To explain it in graphic language, it means placing the starting edge of beta above the terminal side of alpha. At this point, beta's terminal side is alpha and beta's terminal side. Can those two corners be subtracted? To solve this problem, we first need to introduce the concept of inverse angles. Just like the real number a has an inverse negative a, we can also have an inverse angle for an angle. As shown in the figure, we rotate the ray OA around the endpoint O by the same amount in different directions, and the two angles formed are called opposite angles. If alpha itself is a positive angle, then negative alpha is a negative angle, as shown in the left figure. If alpha is a negative angle, then negative alpha is a positive angle, as shown in the right figure. With the concept of opposite angles, we can define the subtraction of angles. Just like in real number subtraction, subtracting a number is equal to adding the opposite of that number. We have alpha minus beta equal to the opposite angle of alpha plus beta, negative beta, so that the subtraction of angles can be converted into the addition of angles. In order to better study angles, we need a unified standard and to better represent the cyclic changes of angles, so we usually place angles in a Cartesian coordinate system for research. For the convenience of aligning the vertex of the angle with the origin and the starting edge of the angle with the non-negative half-axis of the s-axis, what quadrant is the terminal side of the angle in? What is the quadrant angle of this angle? This is the concept of quadrant angle. If the endpoint of an angle falls on the coordinate axis, we consider that the angle does not belong to any quadrant. Let's look at the following example. The starting edge of the 30-degree angle falls on the non-negative half-axis of the x-axis as specified, and its ending edge falls on the first quadrant, so we say that the 30-degree angle is the first quadrant angle. The starting edge of negative 120 degrees falls on the non-negative half-axis of the x-axis, and its final edge falls on the third quadrant, so we say that the negative 120-degree angle is the third quadrant angle. What quadrant angle is the acute angle? Must the first quadrant angle be an acute angle? As for right angles and obtuse angles, please also think about such problems. Which quadrants does the inner angle of a triangle cover? Let's answer the above questions respectively. Acute angles range from 0 degrees to 90 degrees. They all end in the first quadrant, so the acute angle is obviously the first quadrant angle, but the first quadrant angle does not necessarily belong to the acute angle, such as negative 300 degrees. For example, if you add 30 degrees and 360 degrees, the final edge of 390 degrees will also fall in the first quadrant, but they are obviously not sharp angles. A right angle is 90 degrees, and its final edge falls on the positive half-axis of the y-axis, but the angle falling on the positive half-axis of the y-axis is not necessarily a right angle. It may also be a negative 270 degrees, or it may be a 450-degree angle obtained by 90 degrees plus 360 degrees. That obtuse angle, according to the same principle just now, we can know that the obtuse angle range is between 90 degrees and 180 degrees. They are the second quadrant angles, and conversely, the second quadrant angles are not necessarily obtuse angles. Finally, let's look at the inner angle of the triangle. The value range of the internal angle of a triangle can be represented by an interval surface, that is, an open interval of 0 degrees and 180 degrees. It rotates counterclockwise from the positive half-axis of the x-axis to the negative half-axis of the x-axis and experiences the first quadrant, the positive half-axis of the outer axis, and the second quadrant. If the final edge of the angle does not fall in the four quadrants, can you show these angles? For example, can you show the set of angles where the final edge falls on the negative half-axis of the x-axis? When we saw such an angle in the past, we might say that the angle is 180 degrees. Today, after learning, we consider the direction of rotation. We can say that the angle is negative 180 degrees, and the difference between the two angles is 360 degrees. However, if the 180-degree angle is further rotated counterclockwise for one cycle and then returns to the negative half-axis of the x-axis, the angle at this time can be expressed as 180 degrees plus 360 degrees. If this process continues, I can also express as 180 degrees plus twice the 360 degrees. Such a process can be carried out in an endless cycle. So we can finally get it. The method of the set table of angles whose final edge falls on the negative half-axis of the x-axis is that s is equal to beta. Beta is equal to 180 degrees plus 360 degrees of k times, and k belongs to the set of z. Then, if we replace the previous 180 degrees with arbitrary angle alpha, we can get all the angles that are the same as the terminal edge of angle alpha, together with the method represented by angle alpha. That is, it can be represented by the following set. That is, s is equal to beta, beta is equal to alpha, plus k beta 360 degrees, and k belongs to z. Any angle that is the same as the terminal edge of angle alpha can be expressed as the sum of the perimeter angles of angle alpha and integer. Can you represent the set representation of the right corner where the final edge falls on the x-axis? Obviously, this set should be derived from the union of two sets that fall on the positive half-axis of the x-axis and the negative half-axis of the x-axis. If the final edge falls on the positive half-axis of the x-axis, it can be expressed as 0 degrees plus 360 degrees k times, and the angle that the final edge falls on the negative half-axis of the y-axis can be expressed as 180 degrees plus 360 degrees k times. When the two sets are merged, for the convenience of merging operation, we transform 360 degrees of k times into 180 degrees of 2000 times. Then we take this 180 degree and 2000 times of 180 degree out of 180 degrees. We get 2k plus 1 times 180 degrees. At this time, we will observe the two sets before and after. The former set is interpreted as 0 degrees plus 2000 times and even times of 180 degrees, while the latter set is 0 degrees plus 2k plus 1 times and odd times of 180 degrees. Put them together in this way, it is 0 degrees plus an integer multiple of 180 degrees. We introduce a new letter n to represent this integer. We ignore the existence of 0, and finally write that beta is equal to 180 degrees of n times. N belongs to the set of z, which is the set of all angles whose final edge falls on the x-axis. But obviously this process is very complicated. Can we still consider it this way? We choose a point on the positive half-axis of the x-axis, such as 0 degree. If we rotate it counterclockwise by 180 degrees, it will fall on the negative half-axis of the x-axis. If we rotate this 180 degrees counterclockwise by 180 degrees, it will return to the positive half-axis of the x-axis. This process can also be repeated, so that is to say, we can switch back and forth between the positive and negative half-axis as long as we add 180 degrees of integral multiples on the basis of 0 degrees. So we can directly write such a set, s is equal to beta. Beta is equal to 180 degrees of k times, and k belongs to the set of z. Can you now represent the set of all the angles whose final edge falls on the coordinate axis? At this time, the final edge has 4 positions. The difference between two adjacent end edges is an integer multiple of 90 degrees, so if we choose a basic angle x, 0 degrees on the positive half-axis of the x-axis. On the basis of 0 degrees, we can switch back and forth in the 4 coordinate axis directions by continuously adding integral multiples of 90 degrees, so we can directly write its set representation as. That is, beta is equal to 90 degrees of k times, and k belongs to the set of z. So, with the representation of the angle where the end edge falls on the coordinate axis, will you now represent the second quadrant angle? The second quadrant angle starts from the positive half-axis of the outer axis. The negative half-axis centered on the x-axis. The representation of y-axis and positive semi-axis is 90 degrees plus 360 degrees of k times. The negative half-axis of the x-axis can be expressed as 180 degrees plus 360 degrees k times. So the second quadrant angle falls between these two ranges, that is, beta is greater than 90 degrees plus 360 degrees of k times, and beta is less than 180 degrees plus 360 degrees of k times. K belongs to this set. In order to consolidate the understanding of the above knowledge, let's do the following exercises. In the range of 0 degrees to 360 degrees, please find the same angle as the final edge of the negative 950 degree 12-minute angle and determine which quadrant it is. Because the same angle as the final edge of negative 950 degrees and 12 minutes can be expressed as a set, S beta is equal to negative 950 degrees and 12 minutes plus 360 degrees k times k, which belongs to the set of z. You can estimate that when k equals a few degrees, this angle will enter the range of 0 degrees to 360 degrees. Through estimation, we find that when k is equal to 3, beta is equal to 129 degrees and 48 minutes. Obviously, this is a second quadrant angle. When we study the angle of minus 950 degrees and 12 minutes later, we can study it with the properties of the angle of 129 degrees and 48 minutes, which is also the significance of the same angle in our study. Let's take another example. Please write the set S whose terminal edge is on the line y equal to the upper corner of x. In S, what are the element betas that satisfy the inequality betas greater than or equal to negative 360 degrees and less than 720 degrees? First, we draw this line y equals x in the rectangular coordinate system. We can find that the angle between it and the x-axis is 45 degrees. In the range of 0 degrees to 360 degrees, the final edge has two angles on the line y equals x, 45 degrees and 225 degrees. The same angle as the final edge of 45 degrees can be expressed as 45 degrees plus 360 degrees k times, and the same set of angles as the middle edge of 225 degrees can be expressed as 225 degrees plus 360 degrees k times. Then the union of such two sets can get the answer we want. According to the first method or the second method just now, we can finally get the corresponding result, that is, 45 degrees plus 180 degrees of n times, and n belongs to the set of z. So, what are the elements in S that satisfy the inequality beta greater than or equal to negative 360 degrees and less than 720 degrees? How many are there? Let's first look at the range where beta is greater than or equal to negative 360 degrees and less than 720 degrees. This is exactly the range of 3 perimeter angles, and within the range of 1 perimeter angle, there are obviously 2 betas corresponding to it. So within the range of 3 perimeter angles, there should be 6 betas corresponding to it. So we can know that there are 6 beta without calculation. If we want to find these 6 points by means of calculation, how can we find them? Let's start with n equals 0. At this time, the angle is 45 degrees, which is obviously within the range required by the topic. If n equals 1, the result is 225 degrees, which is still within this range. If we let n take 2, the result of 405 degrees is also in this range. If we let n equal 3, the result is 585 degrees, which is still in this range. If we let n equal 4, we will find that this angle has exceeded the range of 720 degrees. When n is negative 1, the angle is negative 135 degrees. In this range, when n is negative 2, the angle is negative 315 degrees, which is also in this range. If n is negative 3, we will find that the angle is beyond this range. So finally, when n takes all integers between negative 2 and 3, it will get 6 angles that meet the requirements of the topic. When n takes integers other than these 6 values, it will go beyond this range. Now let's make a class summary. In this lesson, we introduced the angle of our research object based on the circular motion bearing the periodic change law, and it is extended to any angle, and it is divided into positive angle, negative angle, and zero angle according to the different direction of rotation. We consider not only the amount of rotation, but also the direction of rotation. Add a symbol to the angle and use the symbol to represent the direction, so that the angle has the same quantitative characteristics as the real number, and the addition and subtraction operations between two angles can be carried out as between two real numbers. In order to facilitate, unify standards, and better reflect the law of cycle change, we put the angle into the plane rectangular coordinate system, so that the vertex of the angle coincides with the origin, and the starting edge of the angle coincides with the non-negative half-axis of the x-axis. When the final edge of this angle falls in the quadrant, we say it is the quadrant, and then we introduce the concept of quadrant angle. After that, we studied the representation of the same angle at the end edge. This lesson involves many concepts of angle, including arbitrary angle, positive angle, negative angle, adjacent angle, quadrant angle, and angle with the same end edge. This has a lot of conceptual overlap or intersection with the concepts of acute angle, obtuse angle, right angle, interval angle, internal angle of triangle, and so on we have learned before. For example, we say that the obtuse angle is the second quadrant angle, but the second quadrant angle is not necessarily obtuse. The reason is that when we studied obtuse angle, right angle, and acute angle in the past, we only considered the size of the angle, but now the quadrant angle is the position of the end edge of the angle, which is not only determined by the amount of rotation, but also considered the direction of rotation. It may also be a negative angle, so there will be conceptual differences between the two. Today's content has laid a foundation for our subsequent study of the sum difference angle formula and the induction formula. That's all for this class. Goodbye.